Hello, Internet. Today we're going to be taking a look at one of the more simpler ways to do pathfinding in any project. In this case, we're going to be using Unity 3D, and we're going to be making pathfinding that can find a path between any of these circular nodes that I've created. This supports any number, and it randomly generates a new graph, I guess, every single time we run this. And so we can configure that. I've already done this just to kind of get this whole thing set up. But what we're going to be working with is an algorithm called Dijkstra's algorithm. I'll put a link to what that actually is in Wikipedia. But effectively, the way this works is we're going to find a target node. And so how this is going to work is we're going to have one node where we want to get to. So if you think of like a tower defense game, for example, you want to get to wherever the end of that is. And there may be things in your path that block you. And so what this is going to do is take every node or everything adjacent to the target node, and it is going to find a distance from all of those. And then it's going to repeat that process over and over and over again until you've covered every node. And then each node is going to be assigned the least amount of distance it takes from that node to the target node. And then the way this works is regardless of which node you're at, the next node to go to is the node with the lowest distance remaining. And so that's how you use this to pathfind. And so for a single fixed target, this works really well. So if you don't need to regenerate this, if you need to constantly be recreating this, it becomes a little bit more complicated. But if you have like a fixed terrain or something, this should work. I'm using just random 3D nodes, but this also works with just a grid-based system. It's the exact same thing. The implementation is just going to be slightly different. I don't know if I'm going to share this code because the implementation can depend a lot on what you're doing. But hopefully this is going to cover some of the basics and it's something that you can just go over. I personally find this much simpler than something like A* or something like that. This is probably the simplest way to do pathfinding that I can think of. And it isn't maybe the most efficient or whatever. There's probably better ways to do it. But if this works, it's a pretty straightforward way. We're going to hopefully get it all done in one video. So that should hopefully demonstrate that it's not that difficult. So I have two things set up right now. We're going to walk through what I have so we know what we can build on. So we have the node information, which is stored on each of these nodes. And then we have a node connector, which is actually what connects all of this. It's connecting everything. I've added some gizmos so you can kind of see what's going on. The red are connections. They're bi-directional. So the way the connector works is it actually creates connections from two nodes, one to the other. And so they both will have a connection to each other. That isn't actually required with the implementation that I'm doing. I'm just doing that because that way I know we'll get cycles. And cycles are an interesting edge case in this algorithm because if you don't handle those correctly, you'll get an infinite loop. It will just keep going around your graph forever because it will never reach the end of the graph because there is no end. It's got cycles. So the way this works, we have red lines connecting everything. And then if you select something, it is going to draw blue lines or cyan lines to all of the connected nodes to that node. And it is going to, is this correct? This doesn't seem correct. I should have checked this, but this doesn't look right because we don't. Oh, okay. So there's a layering issue going on here. I didn't really think of that, but we have an issue where I draw red lines and I draw the cyan lines just so that everything works. The problem is we're drawing everything. I can fix that. One sec. So the way this works, we have a onDraw gizmos. And onDraw gizmos selected, there's a to-do to draw the path to the end node. That's going to be like our final product, is we are going to be able to visually draw in gizmos a path from the selected node to the target node, wherever that is. So the way this works is we have the draw connected nodes, which just draws lines to everything. I think we can turn that off for cyan. No, that doesn't make sense. onDraw gizmos. Okay, I don't know what's going on, but we can fix this a little bit. I don't know how. It'll be fine. We'll leave it. I'm sure it's okay. So this one has 7 connected nodes. So that is correct. We're just getting the wrong number of cyan lines. I don't know why that's happening. That might interfere with actually drawing the final path, but we can fix that later. It's just annoying. Anyway, got distracted. Doesn't matter. We're gonna do this. And so what we need to do is select a target node. So I'm going to actually build on top of this node connector. And so what this node connector is doing is it has a list of nodes and a connection multiplier. And that is going to determine the number of connections that each node is going to establish. That doesn't mean it's the total number of connections that are going to exist. But what it is saying is that if there are 10 nodes, we are going to attempt to create 20 connections because our multiplier is 2. And so the way that works is we iterate over all the other nodes, and then for each of number in our connection multiplier, so we have 2, so we're going to do this loop twice. We are going to select every node that is not the current node. So we're going to take the entire list of nodes and select the current node all the nodes that aren't the current one. So we have a list of all the options, and then we're going to randomly select one of those options. And then if we don't already have a connection to that node, we're going to create a connection to this. If we do already have a connection to this, that is just going to be a lost connection. So we're not ensuring that we have 20 connections in this case. We may have less, but that's fine. That's sort of intentional. So this is how all of this ends up working. What we need some sort of target node. And then after we've connected everything, so this connect nodes is sort of establishing our graph. It's creating this actual mesh of things that we want to pathfind across. After this point, we can do our pathfinding. There we go. So we're going to need some place to store a target node. We could either store it in the node connector or in the node information. It doesn't really matter. I'm going to do this by just having a public static node information. And this will be our target node. I'm also going to create, is this the right way to, so this is kind of a hacky thing because again, this is more intended to show this algorithm than it is for you to use this verbatim in whatever you're doing. So we're going to do a public node information, and this will be our target node display. And so that isn't actually intended to do anything. That is intended just so that we have a reference in the inspector that we can go back to. This prevents me from needing to do a custom inspector. So we're just going to assign that at the very end. I'll just leave that down there. It's a hack, but it should work. We could solve this nicer, like with properties. But there's a little bit more work required to actually get that to show in the inspector. And so we're just going to ignore that, not do the extra work and get a solution. So pathfinding, the way this is going to work is we need something. I already have a node distance stored here. So we already have a distance for our nodes. And so the way this is going to work is we're just going to use the distance physically between the nodes. You can do all sorts of interesting things with this. So the node distance doesn't have to be the actual distance. For example, if you're doing like a grid-based game, maybe it's a more difficult move to move across mountains than it is across a plane, for example. And so what you can do is you can set the weight for that to be, say, 1 for the plane and 5 for the mountain. And so it actually takes 5 times more to cross the mountain than it does the plane. And so that can actually influence the entire pathfinding thing. We're not going to do that. We're just going to find the shortest path between the available connected nodes. But again, this is a simple solution. You can expand on this however you want. It really depends on what you're building. So what we're going to do is we are going to calculate distances. And so this actually is, the difficult part of this is not actually calculating the distances. The difficult part is iterating over this without doing loops. And so what we're going to do is actually store something to prevent us from hitting those loops. So we are going to have a list of, let's do this, of visited nodes. And this is going to be a new list of node information. And so that node information, again, is the information about our nodes. And so we have a list of all the nodes, and this will be a list of all the ones we visited. And each of these node informations also has a list of all of the connected nodes. And so we can start at a current node. So what I'm going to do here is I'm going to do a queue. And so this should allow us to kind of do a breadth first search across the entire graph. If we used a stack, it would be a depth first search. That's just sort of the difference between them. It doesn't really matter. We should get the same result either way. It's just the way that we're going to be doing this. So the way we're going to do that is we are going to have a var nodes to visit equals a new. We'll do a linked list. I don't think there's actually a queue, but linked list will do the same thing. We can just treat it like a queue. Nodes to visit queue. We'll make that a little bit clearer, just because I'm kind of not using a actual queue. I think queue might be a thing. Okay, it is. Cool. Then we can actually just use that. If a queue doesn't exist in whatever language you're using, it doesn't always. You can just use a linked list and use append or take first and append last. And that does the same thing, or add to last, or whatever the function is. It would have done the same thing. Queues just make that a little bit more concrete, so you can't do other operations. So if you're not familiar with a queue versus stack, just to kind of cover that as well, a queue, it means first in, first out. And so what that's going to mean is if you think of like a line going up to a ride or something, the first person that gets in that line is going to be the first person to get out of it. If you are from the UK, I believe queue is already the word for a line, so you're already set. Stack is the exact opposite. If you take a stack of cards and you start laying them into a deck on the table, when you start drawing from that deck, you're drawing from the top again. So you're putting things in first, which means they're coming out last. And so it's just the opposite of one of these two. And they have different uses between different things. I talked about depth first versus breadth first search. There's a few other uses for those data structures. We're not going to get into that because this is a tangent that we don't need to explore. But that's that. So nodes to visit. The first thing we're going to do is nodes to visit dot add. It's not add. It's enqueue and dequeue. Those are the actual names of the function in this case. So we are going to add our target node. And so at this point, we need to have a target node. So we need to do target node equals generate target node, which means we need to actually do something here. This should be relatively easy. We're just going to return from the nodes a random range between 0 and the node's length. And that should get us any node randomly from the list. And we will build based off of that. All of this randomness isn't really required in this case. I could just specify a specific node and always pathfind to it. This just allows us to kind of regenerate the thing and kind of see different solutions each time. I could have like hard coded something really simple, but I thought this would be more interesting. So there's no actual need for the randomness. So we are enqueuing the target node, and that is how this is going to work. And so the way we're going to do this is we're going to do a while nodes to visit queue dot count is greater than 0. So while there is something in that queue, it means that there is still a node that we need to visit and process. And so part of this is we are going to calculate the node distance. The node may already have a distance, and so we actually need to check that and say, is the new node distance less than the current one that we're suggesting? So calculate the node distance, and then we want to do something else. Calculate the node distance, and then find available next nodes and queue them. I think there's a little bit of a problem here in the fact that we are going to lose some information. Part of the problem with doing this, where we're using a queue instead of throwing things onto the stack using a call, we are going to run into a problem because we aren't caching the distance. And so we actually can't find the distance back. But I think we have a solution for that. So we're going to rely on that solution and do that. The solution is going to be each node, we can look at all of its adjacent neighbors that exist and just select the next, the lowest distance. So in order to make this work, I'm going to initialize the node distance to a float.max value. And this is going to mean that whatever the max value of a float is, it's some massive number. Whatever that is going to be assigned to all of the default values of a node distance. And what that is going to translate into is when we actually start looking at this, when we compare for less than something, we should get the max distance versus the new value, the initial value. So instead of it initializing to 0 like it was going to do, it's now set to the max value. And that should make these comparisons a little bit easier. The downside is if we initialize this wrong, one of the distances is going to be a max value, and that's not great. It's asking for trouble if we let those stick around, because we start doing weird math on them, weird things are going to happen, especially if we try to add something to it. So calculate the node distance. So the first thing we're going to do is, do we even need to do this? We might as well. I think this will make sense. So we are going to do, well, first we need to dequeue the node. So current node equals nodes to visit queue. Whoa. Nodes to visit queue dot dequeue. So that is going to get us the next element in the list. It's gonna pop something off of our queue, or dequeue something from our queue, and give us that item. So that item is no longer in the queue, and we get the value of it. And so what we're going to do is take that and actually do some things with it. So if the current node is equal to the target node, then the distance is 0. So we can just say current node dot node distance equals 0. So this is like a special case that I'm adding. We could do this outside, but I think it'll be nicer inside of this loop. Again, we can refactor this later, but we probably won't. So current node, that node distance equals 0. That sets that equal to 0. And then what we're going to do is find the next available nodes. So for the next available nodes, that's just going to be equal to var next nodes equals the current node dot connected nodes. So that is a list of all the connected nodes to that node. And so what we want to do next is enqueue all of those. But this isn't actually the available nodes. So we want to var filtered nodes equals the next nodes, where is there a way to do contains? Not really. Dot where, I guess, the node is not contained in the visited nodes. So visited nodes dot contains node. And this needs to be a not. So if it's not contained in the visited nodes, then we can go and visit it. But if it is, we don't want to. So I am going to, because I don't know if I'm going to be actually evaluating this more, this is a link function, which means it's going to be lazily evaluated. So if we don't evaluate it, it means every single time we reference this filtered nodes variable, we are going to be evaluating that where. So we're going to iterate over every node every time we reference it. So if I were to do filtered nodes twice down here, we would do that where statement twice, and we don't need to. It's going to give us the same results. It's just more work that we're doing. And so by forcing it to evaluate, we actually force it to iterate over that now and prevent the lazy evaluation from happening. So that gives us our filtered nodes, and then we just need to add them. So for each nodes to visit queue. Whoa, that's not right. For each node in the filtered nodes, we want to do nodes to visit dot enqueue the node. And so that will add it. The only problem is we aren't actually adding any nodes to this queue. We're not actually doing anything. So what we want to do is say this node has been visited. Is that correct? I don't think it is. What's the best way to do this? I think. So okay, I should talk a little bit about why I'm hesitating here. If I just push the current node in, if I do add to queue and do the nodes to visit queue, or visited nodes, sorry, dot enqueue dot add the current node. The problem with this is after we do the first iteration, it's possible for something else to actually point into that. And so the problem with that is there may be a shorter path in one of those things. And this will prevent us from ever seeing that. We won't actually iterate over that a second time. And we probably want to. And so ideally with a bi-directional, with a directed graph, this would be much easier. Especially if it was acyclic, so you didn't have cycles. Because then we could just say, do all of the nodes leading into this, have they been visited? And if that's true, then we're done. But we can't do that. We can't actually say that. And so I need to actually step back and think about this. So I will be back because I need to figure out when is a good time to enqueue this. And off of the top of my head, I can't say. But if we do this wrong, we're going to get something that isn't necessarily correct. Where this is, it's probably fine. We don't calculate the actual distances for anything, but it's probably fine for like a really, really basic implementation. But because we have something where actually things aren't all connected, where we can get some weird like diamond thing going. And so what could end up happening is if I go up this top path, that's longer than if you went along the bottom. But if we go along the top first, we're going to visit that final node using the top path. And we're going to tell everything, don't go here anymore, even though we still need to go there because we haven't processed it. And so that is, I guess, the problem. So I need to figure out how to do that. And I will be right back after I do that. I think I have made some progress. I was thinking about this slightly wrong. I talked about having that question in the back of my head about how would we calculate the actual distance traveled, because we wouldn't actually know the distance because we weren't perpetuating that. We weren't keeping that in our queue. We were just holding the node information, and we were just enqueuing that and then hoping to kind of derive that distance. I don't think that's a good solution. Instead, we're going to actually have each, as we iterate through this, as we're starting at our target node, what we're going to do is we are going to calculate the distance from that to each of its children. And so that is going to identify all the children and calculate for those children the distance to each of them. So we're going to do that inside of here. And once we know that distance, we can either assign it or not assign it to that node. But because they're non-visited nodes, that should be fine. But because we visited every child as a part of this, we should be able to mark the current node as visited because everything adjacent to it has already been calculated. So it doesn't need to be used in any additional calculations. And so we can just do that down the tree. That is the current thought process. So I think this should work. I drew it out and it seemed like it made sense, and it made sense in the previous times that I've done this. I'm pretty sure this is how I've done it. So we're going to do that. And if it doesn't work, then I'll figure something else out. Or you won't see this video. Hopefully you do though. So visited node or visit the node and calculate the distance. So we're doing a distance calculation. So we are going to do var distance equals blah. So this is actually going to be the calculate node distance. Node distance. So I'm actually turning this into a function, and it's going to provide the current node and the target node. So we give it 2 nodes, and the output of that should be a float. And so all we want to do is do return the current node dot transform dot position minus the node dot whoa. What did I do? Node.transform.position. We want these as a function so we can get the magnitude. And we're just going to return the actual distance. That's all we're going to use this for. But this function, by isolating this, if we want to add more complex things like pathing over different types of terrain, this gives us a way to do that. So that will give us an actual distance. And so what we want to see is if we should assign that distance to the node. So if var new distance equals the current node's distance, so node distance plus the calculated distance, so the distance between the current node and the new node plus the total distance from the current node to the end, whatever that is, that's what we're going to use. And then we are going to assign that if it's less than the node's distance. So if the node distance, we're going to say math.min. So we're going to assign the minimum value of the current node distance and our new distance, whichever one is less. And then at the very end, we'll enqueue that node and say go and traverse that and actually check it. This will prevent us from going back because we're marking things as visited. And since we've visited every unvisited node as part of this, our work is done. We have calculated the minimum distance from the current node to wherever that is. So we should be good. So we can add that to the visited nodes, and that will check that off, and we won't go there again. And so this should hopefully calculate our distances for us. If we've done all of this right, we should be able to actually run this and get something. My computer may freeze because I have an infinite loop somewhere that I didn't think of, but hopefully not. This is actually one of those times when using Unity might not be great because it will lock all of Unity instead of just crashing a program. But it seems fine. So we should be able to find the target node, which is down here. And so this should have a distance of 0. And then all of these should have no distance 0, no distance 0, no distance 0. Uh-oh. That isn't what we want to see. Why are they all zeros? So we're going to do one other thing. Connect nodes. As part of that connecting nodes thing, let's do node.node distance equals float.max value. I'm concerned that it may be stored because I set the default value, but also they already have a value set. So they're clearly not getting that float.max value from them. So if we automatically force it to be the max, we should get results. And so we do. We get 20 here, 18, so that's a little bit closer, 9 much closer, and then this one, nope, further away. And there's our target. So we actually were able to kind of do the same pathfinding algorithm ourselves, to actually find the target. If we click any of these nodes, we'll see this is at 27. So we need something less than 27, and that means we're getting closer. 31, that's not closer. 21, that's closer. And then we can find the next one that's below 21. So this is 8. That seems pretty good. But this is also connected over here. That's 9. So we're going to take 8. And then we look for the next thing, which is this one. This is 20. So that's moving away from it. That's not connected. And that's back to the original node that we were at. So we know we need to go here, and that's 0. So we've reached our target. And that's how this ends up working. So it seems fine. It seems like we're actually getting the results that we expect, which is good. Now, the fun part, we're going to actually render, when you select a node, we're going to pathfind back to that node, or to the target node. And so the way we're going to do that is going to this node information. So this isn't going to give us like a fun path list or anything. This is going to be like a really scrappy, let's find 0. That's really what we're trying to do here. So on gizmos selected, we want to render path, or we're doing draw. So let's do draw path. And we want to draw the path to the node node connector dot target node. That's why we made it static, so I could make that one call. It's the only reason. Draw path, that's where we're going. And so what we want to do is just find that path. So we're going to do gizmos.color equals color.orange. There is no orange. That's unfortunate. Yellow. All right, cool. Gizmos.color is that. Now we need to find the next path. So we are going to iterate down this. I think we can do this with recursion. I hesitate to say that, but I think we can. And if we're just working for like a scrappy thing, this will work. The cues that I showed are a way to avoid using recursion. If recursion is effectively just a stack with some extra call information, so you preserve the scope. If you want to just do recursion, you can usually substitute with a stack or a queue, depending on what your intent is. But we're just going to do recursion because that isn't really the point here. So what we want to do is find the lowest node. So we're just going to store the node, var node equals, it doesn't matter which one. So we just need connected nodes.first. Sure. It really doesn't matter. We could just index to 0, but I'm going to do first because we're writing it out and it's a little bit easier to read. So we have the first node, and then we just want var distance. We don't even need that. We have the node. The node has the distance, so we don't need to actually store the distance for this. All we need to do is do for each var connected nodes. Is there actually... Can I do that? Can I just do connected nodes dot? Yeah, I can. I can just use link for this. So we can actually just do connected nodes dot min, and if we give it a condition, it will find the minimum value of all of that. So we're looking for the minimum distance. So I can just provide in a node and do node dot node distance, and that will return us the node in that set with the least node distance. We could do max, it doesn't really matter, but we need the lowest. We're trying to get to 0. So that's going to be the next node to iterate on. And so what we want to do is draw a line to it. So we are going to do a gizmos.draw line. I'm going to do it from this transform.position to the node dot. Why is this a float? Oh no, it's finding the minimum node distance. Oh, this isn't going to work. How does this work? T source, T result. I don't think we can use this. Maybe we can. So if I implement a selector like this, source like that. So we're giving it a source thing, and we need to return something. So we're just going to return the source. Okay, it doesn't like that. This is a part where we get confused. Okay, really doesn't like that. We can't do them in. I tried. There's probably a way to do this with link. I thought I knew it. I don't know it. I thought there was a way to do that, but whatever. We're just going to do the first and do this the old-fashioned way. So for each var n in our connected nodes, if n dot connected distance. Oh, that's not right. Dot node distance is less than the node dot node distance. Then we want to do something. So we are going to say node equals n, and that's it. That's the entire loop. I should use something other than n. We will. Sure, node information. That'll work. Should mention I'm using ReSharper in Visual Studio to kind of help me out here. A lot of these refactorings and things are kind of coming as suggestions from that. But we want node.transform.position. And that should draw a yellow line between everything. The only thing we need to do next is recurse through this. So we have the node, so we just need to do node.drawPath to the target node. Why do I need the target node? We're not actually doing anything with that. We can just drop that. We've already calculated what the target node is. So as long as the target node doesn't change, if the target node changes, the distances have to change. Otherwise, the distances don't mean anything. And so we can just rely on the distances for this. We don't actually need to provide a target node. That isn't needed. So we can just draw the path that way and then recurse until we get this. If the node is not equal to the what's the call? Node connector dot target node. Otherwise, we'll get an infinite recursion. With every recursion, you need some way to exit it, because if you don't, you're just re-invoking something, and that's how you get infinite loops. So we need some way to break out. In this case, it's this if, where if we hit the target, we're done. We don't need to draw a line at the target to the target, because that's what's going to happen. So we're going to avoid that and do all of this. And this should get us a line back to our thing. We had some overlap, so it might cause some issues. Sequence contains no elements. That is a problem with this. So if connected nodes is empty, what? There is no is empty? What? Okay, dot count is equal to 0. We're just going to return. So that gives us another out. This prevents us, because we generate things at start. During the editor part, this actually isn't going to work. So we should be able to run this now, hopefully, and get no errors. And there we go. And there is our path here. So that must be our endpoint. So if we go here, we get rendering errors. There we go. There's the yellow. I can fix this by offsetting these slightly. It's not a great solution, but we're kind of just drawing things on top of one another, and that's causing a whole bunch of weird issues for things to draw over one another. So what we can do is take this position and just do plus vector3.1 times 0.05f. This is a hack. And if we were doing this for real things, we could make this better, but it's not for real things. It's for video. And we don't care about drawing gizmos. That isn't the point. So this offsets things just slightly, so we can actually see. Stack Overflow. Uh-oh. Those aren't good. What do we do? Crash Unity. That's what we did. It doesn't want to respond. Oh no. Okay, so something I did causes this to crash when we restart it. So it recompiled, and that caused us to lose some of the information that was stored when you start. That stuff gets dropped because it isn't serialized by Unity. So when you recompile everything, all that information drops out. And now we have a Stack Overflow and Unity's unresponsive. So I will be right back. I'm going to fix this, and then we will have this working. I may have a different scene because this isn't saved, so it's going to go away. We didn't lose everything, which is good. But we're back. I thought I had a clever solution for this, but it just crashed Unity. So now we're here, and we're going to rerun this, and hopefully we don't get any more Stack Overflows. Cool. So the problem was refreshing things. I'm imagining we had issues because of the recursion. I would imagine that caused the issues. But this gives us our fancy little thing. So we get 0. For some reason, there's a line going back. That's because we're already at the target node. And this check is all the way down here. If I brought it all the way up, it would fix it. We could actually do that. We could have 2 different ways to return. So, or the node is not, we don't have a node. If this is not equal to the node connector dot target node. So if we're not the target node, you can do that. I just created that Stack Overflow again. Oh no. Okay, stopped it. Cool. I thought bad things were going to happen, but they didn't. That's good. This should do the same thing as we were doing previously. It just means we'll actually call into that and then immediately exit. And slightly less good, but it means that if we've already selected the target node, it's not going to find the closest node to it and kind of give you the idea that there's like some other target node. It's just going to be the target node. So if we go back here, hopefully we can just run this and just start clicking on things and get paths. That's sort of the hope. So that's not right. Also not right. Also not right. Also not right. This is wrong. This should be equal. If it's equal to the target node, we're just exiting everywhere except the target node, which is not what we want. So that was an interesting thing. Almost crashed Unity again. I need to stop editing things while my game is running. But there we go. So I'm guessing this is our target. There we go. So we should be able to click anything here, and you can kind of see how we're pathing. This is the basics of pathfinding. The actual code for doing it was like 20 lines. It's a little bit more on the complicated side as far as code goes, because there is actually some algorithm stuff that you need to pay attention to. Otherwise, bad things will happen, or you'll overwrite something and not get the correct information. But it's actually not that much code, and we could cut this down to make it a little simpler with some refactoring as well. But hopefully this is easy, or not easy, I guess, but hopefully this is something that you can use. And if it isn't clear, or there's something that I can do to help you implement this in your game, let me know, or consider joining our Discord. We have a whole bunch of people who are happy to help both share their cool projects and hear about your cool projects. So if you need help learning something, or want to share some of the cool stuff you're building, that's a really good place. There's a link in the description and on the channel page for this, so you can go and check that out. But other than that, I think this is it. So we might do some more stuff with pathfinding. I don't really know, but this is sort of one of the ones where if you're struggling to get into pathfinding, because it is one of those daunting things, especially if you start like looking at A-star or one of those more popular things, it's not super straightforward. There's a lot of technical things happening to make that work. And so this makes it hopefully fairly straightforward. At least the general idea is fairly straightforward. I'll link to the Wikipedia page for Dijkstra's algorithm, but it is very on the technical side, and that can kind of make reading it a little bit difficult. I would recommend, if you can, find other blogs or something that go a little bit into this in a more friendly language if this wasn't helpful for you. Because the Wikipedia page is very much a technical guide to how to like implement the algorithm, and here's some pseudocode and things like that. If that's your style, cool. But for me, that's just a lot. So this is it. I'll leave it here, and thanks so much for watching. So until next time, see you, internet.